The nature of the New Zealand Space Challenge for 2018 is to use new or current technologies or data in space or on the ice to find a better method of identifying hazards and getting across the ice, or to design or prototype new sensor systems or algorithms to help vehicles navigate across the ice in Antarctica. With our legacy of technology, analysis techniques, and operations, we think that we're well along the path to demonstrating such a capacity. In order to safely cross the ice, it's not just a matter of knowing where the explicit hazards are. The crevasses, of course, the smaller, the more dangerous. But it's also to identify areas where the travel is going to be slow. The longer that you're out on the ice, the more dangerous it is, and the more prone for errors to occur. Big things that can slow you down is actually water within the snowpack, or having fluffy, low-density snow. So these are things that any traverse across the ice needs to identify well ahead of time. The surface of the ice responds to transmitted radar waves through both reflecting energy with coherent returns and scattering incoherent returns. A downward-looking system can see both of those types of returns. Now, the reflected energy corresponds more to the dielectric contrast between the medium that you're irradiating and the air. The scattered energy reacts more to the roughness and the structure of that medium. Together, they can inform you where you may have hazards on your traverse route. The side-looking SAR systems, as commonly fielded in orbit, are typically high frequency and they're side-looking, so the reflected energy actually just bounces back off into space and you lose that information, which makes it challenging to untangle the effects of composition, of density, and the effects of roughness. With a nadir pointed system, as we fly in Antarctica on that aircraft, we can untangle these two signatures. The University of Texas radar has a long legacy, extending back into the 70s for some components. However, we have steadily upgraded the system over time and is now nearly entirely commercial off-the-shelf products. Our 60 megahertz radar system has been the heart of our very successful international collaboration over the past decade, IceCap, which has mapped large components of East Antarctica. The radar system has also been, through a number of business contracts, been sold to a couple of national programs. We have that track record. We have also trialed it in multi-frequency mode. It is currently being part of the payload for NASA's next Outer Planets flagship mission, Europa Clipper, bound for Jupiter's mysterious moon Europa, which is thought to be a potential habitat for astrobiology. One of the goals of the mission is to look for appropriate locations for a lander. Our goal is to get this radar system onto drones, autonomous platforms. One step along the path has been to work with our Korean colleagues and Helicopters New Zealand in order to produce an autonomous standalone version of our radar, which we have successfully flown over Nansen ice shelf and over some of the ice shelves of the Amundsen Sea embayment. We have also demonstrated drone technology of the type that we will want to migrate our radar to. In 2016, working with the Australian Antarctic Division, we demonstrated a Tiburon drone from the Wilkins Aerodrome on Law Dome. This is a prototype for a system that has scalable to much larger size, compatible with our radar antennas, and longer range.